Hi class, this is the second part of the recorded lecture from the last class to talk about the load factor and the loss factors. As you probably have seen it in the class, that I draw this picture with two circuit breakers, actually one circuit breaker and one recloser. They look the same shape, they have the same function, and the reason I do that is for you to get the perspective about how this metering data can be acquired from. So the circuit breaker have that metering infrastructure that will measure three-phase P, Q, V, and I, and the same thing for recloser P, Q, V, and I. And what you can see here is that the benefit of having additional recloser is that is twofold. One is the circuit breaker might not be able to see the fault when the fault occurrence is far from this feeder head. And the other part of it is that when the recloser, let's say that you put this recloser here, and there's a fault occurring somewhere downstream of this feeder, and they see it right away, and so it tripped. So what it means is that there is instead of tripping the entire feeder, this recloser actually stripped a small subsystem of that, and as a result, the customer between circuit breaker and recloser is pretty happy because they are not being electrically disconnected from the entire from that fault occurrence which is happening down the feeder. So, but this is only the general concept that I would like you to see, get a bigger picture about what's going on in real system, is that they are mirroring data in the primary network, and you know the power gotta be flowing through from the substation level all the way to our off customer. So which means that if this is a feeder that is operating in radio configuration, then whatever you measure here at the feeder head is got to be the total power, which we can relate that into one single lump load as, say, if the P is equal to 2.56 megawatt, then we know all the data from this breaker. So we can get the statistic like every 3 seconds from this SCADA system. By the way, these are the SCADA system. So if you accumulate every day, every week, and every throughout the year, you have the average number that whatever period you would like to know, and the maximum associated with that period of time. So that will that's something that's something you can relate to the load factor, which is the average divided by maximum. As I said it before repeatedly, the max mean, same thing for the loss factor, mean max. So that is the number that should be equal to 1 or less than 1, because the average will bring the number down, whereas you never get to the point that is more than maximum value, because we are doing the averaging for the denominator value. However, to relate this loss factor to load factor would be something we know, because loss is sort of small proportion of the loading condition. It will be the same pattern if we know that what will be the load at the substation. So from the SCADA standpoint, you should be able to get the averaging and the maximum value. The only thing that we might not know is how do we get the average loss and maximum loss. Even though you may say that, well, I can get the P from this and that P from that value, I do the difference, then I know the loss. Well, it's not quite true for this in this regard, because the loss will be only a small portion of that difference, because the rest of it will go to all the load here. So it's very difficult to measure the power loss based on the information given from the SCADA instrumentation. Like in this case, you have circuit breaker and recloser. That's the reason that motivate us to further investigate the relationship mathematically with the load and the loss in this case. So this picture shows you a simple waveform here, just to indicate the relationship between the load and the loss. And you know you have the two period of time that you have minimum value PL1 and then the maximum value PLD2, and the averaging simply the half of this two periods, presuming that T is the halfway through of the capital T entire period of time. As you can see, the waveform here is pretty much the same shape as the power loss waveform, except that the difference is the power loss magnitude will be significantly smaller than the load waveform. So you can see that this is a pretty good, this is a typical waveform for the load and the loss. So to relate to this, the load and the loss, as I mentioned, I drew a lamp load here just to indicate that this lamp load is representing the entire curve of the load curve. So by definition, average divided by max, right? Same thing for this case, average, PLD average divided by PLD2. 2 is the maximum value. And then if you go through this geometry, it will lead to this situation where you have PLD2 times T, PLD2 times the T plus the PLD1 times the difference between this segment, capital T and small t, and then divided by the y-axis, which is the max value, times the t. And when we have this equation, you can simply simplify this into the next line, and everything will be the same for the loss factor, except that what we are trying to do here is to get rid of loss power here, because we can't really easily get the value from loss power 1 and loss power 2. So what we do here is trying to replace this variable with something else we know. And recall what you have learned from the circuit 1, the power loss is actually I square R, right? So power loss PLS equal to I square R, and the load of the power is P load equal to V times I. The reason I organize in this way is because I want to replace this I into this so that eventually we will write the equation as PLS equal to K times PLD2. So this is a load power and this is a loss power. So it's a certain proportions of this K value with respect to the loss square. So we replace this value PLS with PLD, which is something we already know. And then yet the K here is kind of tricky because we don't quite know what would be the K would look like. But this is making some progress. We are making some progress to relate this so we can move on to the next step the same way how we simplify the last equation. As a result, PLS is equal to this triangular equation here, T small t divided by capital T plus PLD1 PLD2 square. So the red color square here is a key. To simplify our finding, we can divide those two equations into three simple cases. Case 1, case 2, and case 3. So case 1, basically what we do here is that, let's say we don't have power load at all, PLD1 equal to 0, then P loss is equal to 0, right? When load is 0, then loss is 0. So this is a 0 off-peak load, and when PLD1 is 0, then you're going to have to replace that PLD1 with 0. As a result, this is the entire whole thing. Second term is 0. So the same thing for the power loss. So you can conclude for case 1 is PLD, the load factor equal to small t divided by capital T. It's the same as the loss factors. Now the second case is very short period of time when peak of the peak. So t will be equal to 0. So we know that when we replace small t equal to 0, this is 0, and t capital T divided by capital T will be 1. This is 0, the first term, so eventually it will be PLD1 divided by PLD2. Not for the same for loss factor, because loss factor have that square, remember? So even though we have this 0, but that result of this term to 1, that same thing 0 for this term, we have that square term here. So we can simply relate that the loss factor and load factor will be PLD equal to P loss factor square. The last case will be steady state case when t, the small t equal to capital T. So if you do that and replace it to that equation, put it in capital T here, the first term will be 1, the rest of it is 0. Same thing here, when t minus t, capital T, what I mean by capital T minus capital T, the second term will be 0. So we can say that the P1 over P2 will be always smaller than 1 from the this equation and that equation that I put the notation here, the triangular and the asterisk equation. So we can infer that the loss factors and the load factor relationship from those three cases, which is between 0 and 1, we know that those got to be 0 and 1, and they cannot be greater with equal value. So because this is when there is a loading condition, it got to be some value, and if this is got to be some value, the equality here is going to be never be equal to 1 or 0. So how do we prove that this is correct from this study? We break them down into two places, A and B, right? The square of the load factor will always be smaller than the load factors, because the load factor will never be greater than 1. So in this case, you have 0.8 times 0.8 will be 0.64, which is smaller than load factors. We know that the relationship of loss factors will be somewhere in between the two, so we don't know if this is true or not. So for the next couple of pages, we go through this two parts of the proof to make sure that this equality is true. And I don't think that I had to convince you this is something you don't know. So this is a proof of the left hand side of equality for the part A. This is all the way going through it, and you can go through this step as I shown here. The same way for the other equality for part B, the same way. So we prove that from this two page that the load factor square is always equal to less than loss factors, and the loss factor is always equal or less than the load factors. So to conclude all this is that this study will be better off we relate the loss factors with load factors, because we know how to measure load factors. And there are some empirical study in the literature. You probably will see it from the IEEE, that you can see there's a 0.3 and 0.7 model for urban areas. So you can see the load factor times 0.3 and then the load factor times 0.7 to the power 2, and then there's another sensitivity model for the rural area. Overall, you can relate that the load factor FLD and the loss factor will be these two major curves, right? The purple and the red one, and the load factor square will be somewhere between these two. So the bottom line here is that we know that the loss factor must be between the load factors and the load factor square, right? This relationship can be adjusted. The blue line can be adjusted more toward the load factor or more toward the load factor square, except that there are some sensitivity analysis we will be going through a lot, but this will be outside of this class to do this kind of empirical study. We don't have the data, so if you want to do planning in the future for utility distribution network, I think this will be the relationship. We will know that the load factor and the load factor square got to be the upper bound and lower bound of the loss factors. And how accurate this loss factor will be between these two is a study of empirical research that requires some data from SCADA system. So I hope this recorded lecture will help you to better understand how this system is being performed, and with the limited metering infrastructure we have in the distribution system, sometimes we will have no choice but to infer information from the source that we can easily obtain the data set. I'll see you on Monday. Thanks.